after he finished texting.
Hello, can you hear me? Yeah, okay, great. So, where do I start? Today, we don't have a lot of time. So I'm going to introduce you to FusionDB. But obviously, this is a conference. So this is a conference-based talk. It's not a product pitch. And I can't cover everything because there's vast amounts of things I would like to talk about. The people that were unfortunate enough to come to the unconference yesterday heard me go on for about an hour and a half with lots of demos. So today we won't be doing demos, but we'll look at the sort of design, architecture, and why it really came about. And then we'll look at sort of two key components of FusionDB, which are actually some of the earliest components we had to build. So why did I decide to build FusionDB? So back in about 2014, I'd been working with native XML databases for a very long time, and I was unhappy. I wasn't happy with the open source offerings, and I wasn't happy with the commercial offerings for quite different reasons. But I'd spent a lot of years of my life working in this area, and I felt that I needed to do something about it. So I had the opportunity to quit my consulting job and start working full-time on a project of my own design, effectively. It also helped that I had a commercial partner that very much wanted to see improvements made to open-source native XML databases. So back in 2014, why did I feel that this stuff wasn't really working out? The main thing for me that caused me a lot of late-night issues and support calls and problems was correctness. So the database unexpectedly crashing or losing data, or after it's crashed, it wouldn't restore itself to sort of a good state where the user could continue. And if you get enough of these late-night support calls over enough years, you get quite fed up with this. And then the other thing that was really important to me was stability. So there were cases where the database wouldn't crash, but it would just become unresponsive. And it was like this little black box that was sat there doing something, but you had no idea what it was doing. And you couldn't really figure out why it was doing what it was doing, if you knew what it was doing. So not great. So I decided enough was enough after about 10 years. Something had to be done. So I quit my consulting job, finished my beer, and decided to work on this full-time. So the first thing I decided to think about was, can I fix an existing native XML database? Wouldn't that be easier than building something from scratch? So I looked around at the existing open source projects, and I measured them on a number of criteria. And of particular importance to me personally was how quickly I could move. So if I sent in pull requests, they needed to be reviewed quickly. Were there other people in the project that if I sent very complicated pull requests, could they understand what I was trying to do? And ultimately, I felt that I couldn't operate inside one of the existing open source communities in the way that I wanted to move forward. It was just going to be too slow. So I decided that I had to sort of break away, okay? So we decided to build something new, and initially, because we're not marketers, we're software engineers, we didn't know what to call the thing. So we just called it Project Granite, and it was very much a research and development effort. So if you've seen anything from me on the web or anything about Project Granite, that is what eventually grew up to become FusionDB. So initially, our focus was very much on correctness, more so than stability. We should never, ever lose data. And then secondly, of course, we have to be responsive. So the database should never stop answering questions from users or administrators, more importantly. We had a few other requirements that we wanted to meet, one of which is that we wanted to be compatible with something that's already out there, so that it wasn't a giant leap for people to adopt FusionDB. Now, a lot of you will know my background with exist-db, so that's where a lot of my experience has come from over the years. So I decided to start by forking exist-db. I felt that I could create, I don't know, the bastard stepchild of exist-db that would be sort of exist-db compatible, so anybody that uses exist-db could use it, but wouldn't have some of the problems that I perceived that I had with exist-db. Although it became much, much more than that. So the first thing we decided to do was probably the hardest, which is that we weren't happy with how the storage engine in exist-db worked. We spent quite some time auditing the code and really trying to understand how the storage there works. And there's sort of two things that worried us predominantly. One is the architecture of it wasn't going to scale. So it very much will only do one thing at once, and that is either a read or a write. You can't have multiple reads happening at the same time. When we looked into the provenance of the thing, we discovered that it had been around for a very long time and sort of been slowly patched up as it went along. And some of those improvements were really quite good, the caching particularly. But it wasn't going to give us, working on it and trying to improve it, wasn't going to give us the giant leap in sort of performance that we wanted. Alongside that, until recently, I'd also discovered, these have now been fixed, by the way, but other bugs that still existed in the storage engine from 2001 that could lead to data corruption. Now, not everybody's necessarily hitting those edge cases, but the fact that those bugs are there is quite worrying. So we had low confidence in the correctness of this thing. So what did we do? Well, first of all, we'll go on a little detour. So how the hell does an XML database store XML anyway? We should probably try to understand how this works. So if we take some very simple XML, I'm sure most of you can probably understand this. Okay. Anybody struggling with this? Okay, good. I'm at the right conference. Okay, well, I expected that. So the first thing that we do with XML, and this is how exist-db works, is the XML that we think of is really kind of a tree, okay? So behind the scenes, we're really representing this thing as a tree, and then what we do is we go and we number all of the nodes. So these little things in the square brackets are the node numbers. And this uses a very, very clever numbering scheme called dynamic level numbering, which is not something that we invented. It's from a French researcher. And I forget his name, apologies. What this DLN gives you is it gives you the ability to very, very quickly jump between nodes for lookups and navigation. So for example, if you look at this node, you realize if you block off the last digit, you can find the parent. Okay? So if you drop the 0.1 at the end, well, 11, that's the address of the parent. Okay, all of its children are prefixed 111. Okay. So when all of these things are laid down on disk, and you have these long binary strings that describe these IDs, they're encoded in such a way that it makes it very quick to navigate from one node to another. So that's the first thing that we do when we start storing this fruits XML. Oh, we also allocate an ID to the document, but that's just a number. So it's like 6, 7, 8, 9, whatever document you're storing. Second thing we do is we extract all of the symbols. And the reason that we do this is, firstly, if we want to compare two nodes to see if they're the same, comparing the one with symbol 2 and the one with symbol 2, comparing two integers is much, much faster than comparing the two strings fruit. Okay? So we get faster comparisons between node names. And then secondly, it gives us a very simple form of compression. So we're only storing the labels, which are the element names, the attribute names, once for any documents that you store. Find my place. Yep. So the last thing that we do is your document that you've given us, your fruits XML, gets stored into 3 separate files on disk. Okay, the first one is the most important one. This is what we call the persistent DOM. And this is really a B+ tree here. If you haven't seen a B+ tree, don't worry too much. But the point of a B+ tree is it's not very deep. Okay, so it tends to spread outwards. And the reason for that, which is good, is because the index of the B+ tree is in memory. So you can quickly locate the node that you want and then find the page value on disk very, very quickly. So B+ trees are the bread and butter of databases, okay? And they enable you to find the things quickly. And the reason these things are down here is because unlike a B tree, in a B+ tree, the actual values don't live in the tree. They live in page files on disk. Okay? So that's the linking between those things. So that's where your XML is really going. All of your nodes are in there. And then secondly, the symbols that we extracted for the symbol table, they're just laid down one after another on disk. Very, very simple. And then thirdly, exist-db has this notion of collections, and we need to know which documents are in which collections. And that is another B tree. And the B tree has an entry for a collection, and it has an entry for a document. So all your collections and the documents that are in those collections are all laid down on the B tree. And that is, at the simplest level, how exist-db stores all of its data. There are a number of other B trees for indexing and inverted indexes and such, but this is all you need to store XML in exist. So having decided we're going to throw that away, we decided, OK, we've got to build this new storage engine. But we could build our own, but that's kind of hard. Lots of people have gone before us and not done a very good job at it. And this isn't just a reflection on exist-db. When we started looking around, we discovered that, for example, Cassandra, Mongo, DB, and Oracle have all had problems in their storage engine where it's been losing data. Not necessarily today, but in the past, over time. And they have some very, very clever engineers. So, OK, we have some good engineers, but if they have good engineers and they're losing data, how do we know that we're going to get it right if they failed? So what we thought we would do is look around for existing engines that are well proven. Okay? So not just they're available, but they've actually been battle tested over a long period of time with good unit tests as well, and we know that they're stable. So we started looking initially for B+ trees that were implemented in Java databases. And what we quickly discovered is that it was almost impossible to just extract the B+ tree part from someone else's Java database without taking a lot of the rest of the database with it, because they never designed their storage engine in a way that it could be taken out and used in another project. So things like configuration were convoluted and were down into the B tree as well, and we didn't really want to adopt how they configure their database. We then looked at basically pure storage engines that were available in Java. We only really found one, and it had a lot of known issues, so we threw that out. Also, you have to remember that this was 2014, 2015 when we were doing this, so there were less choices available then. But what we ultimately decided upon was RocksDB, which I'll talk about a little bit in a minute. And the interesting thing about these, obviously, is they're all in C and C++, and exist is in Java. So we had to write quite a lot of interesting code to glue these things together. So why did we adopt RocksDB? Well, there's sort of one really big reason, which is Facebook. So has anybody used Facebook? Anybody still using Facebook? OK. So almost every interaction that you have with Facebook, whether it's Messenger or it's Instagram or it's the Facebook website or something else that is part of the Facebook estate, the data for that will be stored in RocksDB. Okay? So RocksDB basically powers the entire Facebook infrastructure. So even when Facebook talk about MySQL, they use something called MyRocks, which is MySQL with the storage engine replaced with RocksDB. When Facebook talk about MongoDB, they're talking about MongoRocks, which is MongoDB with the storage engine ripped out and replaced with RocksDB. All of their storage is pretty much RocksDB. So this gave us a lot of confidence that this thing is really being used by a lot of people and tested. Okay. And then the second reason we adopted it is because it has a really, really rich feature set. So it stopped us from having to build vast amounts of complicated low-level technology, which wasn't beyond us, but these things take time to mature and to get right. And we felt that we could get off to a running start by using something very rich that already existed. So we have our new storage engine. How the hell do we put XML into it? And there's a pun in here, if you know where I come from, where I live, but I'll let someone tell me what that is later. OK, so how do we store XML in RocksDB? We do very similar things to what we were doing before. So we still take the tree, we number it, we still extract symbols. And ultimately, we end up with key value pairs. Something that I neglected to point out, sorry, is the key value pairs. So in this diagram, these things in these boxes are the keys. These identify the nodes uniquely. Document 6, node 1121, and this is the value. So this is a key value pair. So the B tree is storing key value pairs. All storage is really kind of key value. Yep. So instead of storing the key value pairs into exist-db's B tree, we simply put them into RocksDB, which is a key value store. It's an embedded key value store. So RocksDB has this concept of column families, which are basically little mini databases. So for the persistent DOM, we created a column family, a mini database. For the collection store, we created a mini database. And then for the symbol table, we created 3 mini databases, because we not only wanted the symbols, but we wanted fast lookups. So we have an index, which is another little mini database, and we have an inverted index for going the other way, another little mini database, or a column family. And the neat thing about RocksDB and the way it works is that commits in a transaction are atomic across multiple column families. So we can stage all of this information that we want to commit into these multiple little mini databases, and then atomically ensure that it's written to disk. Okay. So I sort of showed you exist-db, and it's a B tree, and how that's laid out on disk. RocksDB is not a B tree. It's a log-structured merge tree, which is quite a different data structure / algorithm. And I don't want to get too much into how this works, because I could go on for hours about this. But simply put, all of your reads and writes happen on this mem table, which is in memory. Okay? And the size of these things are all configurable. This is, by default, what we're using in FusionDB. So when you write, okay, it just goes straight onto this table in memory, and it's written to a log on disk. Okay, so you're never actually storing the information onto disk. Eventually, it gets flushed to disk. So when the mem table of 64 megabytes becomes full, it's written to disk. A new mem table of 64 megabytes is there, so your writes keep going into memory. And then as these files in level 1, so that's 64 megabyte, so it moves down to level 1, and we have a number of these. And as we reach our target, as more data is written, as we get more and more SST files, as we reach this target, some of these will be gathered together and compacted into a larger file and laid down in this level, which frees up space in this level, and it goes on and on and on. And the reason for that is that when it's compacted, you can rearrange things and delete old keys that are no longer there. Okay, so there's a whole process about how this is laid down. But ultimately, if we go back to our fruits example, this is what one of those little SST files on disk looks like. It's just blocks of key value data. And there's some meta filter and indexes and things in the file, but that's not too important. That's mechanics. And I should mention an SST file is what we call a sorted string table. So everything is ordered, okay? Which is kind of perfect for an XML tree that you've serialized, because it then takes on this order. And here's our XML. So we've got our apple, so that's fruits, fruit, orange or something, I forget. And it's laid down like this. So if we want to scan our SST file, because it's sorted, it's very, very quick to reconstruct a document or to pull out a subtree. So it's quite a nice fit for XML, actually. Okay. So that's the first thing that we tried to conquer, was the storage. And then the other sort of fundamental thing that we had to sort out once we had all our XML going into RocksDB instead of exist-B tree was transactions. And I say we had to sort it out. I wanted to do this. I wasn't happy with how transactions were working previously. So who's aware of ACID transactions? Okay, like half the room. Okay, so ACID basically describes the properties of a database, how strong it is with regards to storing your information and performing operations on that information. And one of the important concerns is the isolation level. Okay? And what that really means is when you have concurrent users operating on your system, it describes how those users interact with the data if they're both working on the same piece of data at the same time. And classically, there's been 4 ACID isolation levels. where read uncommitted is the weakest, and serializable, which is typically what is required in intensive finance applications, is the level serializable. So I wanted to provide a level for FusionDB that was as close to serializable as I could get without killing performance. So what we ended up with is, due to a lot of the features that are built into RocksDB, we have what we call snapshot isolation, which sits just below serializable. So it's almost as strong as serializable. And we're looking at adding serializable later. But what snapshot isolation basically does is, when you begin a transaction in FusionDB, you see a point-in-time consistent view of the database. Okay? And that view is immutable. Okay? So how do you update things? Well, when you perform updates, we actually stage them in a write batch in memory. And that belongs to the transaction. So no other transaction is seeing the writes that you make. And they're not written to the database yet. They're all purely in memory, which is nice because it's really fast. And if you want to abort the transaction, we just discard the memory. It's a really very, very cheap operation. It's only when we have to actually persist the write batch to disk, when the transaction commits, that we have to do any I/O at all. So we have some advantages there. I don't think there's a lot more to say about that. So in terms of the APIs that we have, we've obviously inherited, we have a couple of our own custom FusionDB APIs, but we've obviously inherited a lot of exist-DB's existing APIs, which are really nice. So how did we fit transactions around these existing APIs? None of these existing exist-DB APIs have functions or calls for managing transactions. So we simply decided that each API call would be a transaction, which is auto-committed when it completes, or auto-aborts if the API call throws an exception. And that seems to work quite well with how people have traditionally used exist-DB, or that's what we're finding. I hope that continues. And then with regards to xQuery, obviously an xQuery is made up with multiple statements. So we had to decide whether each statement within an xQuery should be a transaction itself, or whether the entire query is a transaction. And there's probably some other models in there as well. But today, for compatibility with exist, we decided that a single xQuery is an entire transaction. So if you have multiple statements in your xQuery and you're writing to the database, if any one of those errors, the entire thing is aborted, so nothing changes in the database. And historically, that has been a problem in other native XML databases, where maybe some of the data is in the database and some of it isn't, because the error happened halfway through your query. We don't have that problem. And then we thought, well, we have this facility for sub-transactions, and they're kind of fun. How can we expose those to the xQuery user? And we realized that try-catch from xQuery 3 is quite a natural fit for this. So when you start a try block, it begins a sub-transaction. So if you throw an error inside your try block, it only aborts the operations that you performed inside the try block, falls back to the catch block. Okay? So if you want to try and make a web request and store a document and that fails, you can recover from it without modifying the database in any way by wrapping things in try-catch. And you can nest try-catch, obviously, in xQuery, so we allow you to nest sub-transactions. So you can sort of go arbitrarily deep with these sub-transactions as well. Okay. So I demoed some of these features the other day. I'm not going to reiterate on those right now. But what I will mention is the one that I'm particularly happy with, that I really love, is the checkpoint backup. So we have a facility for doing an instantaneous backup of the database, because the SST files on disk are immutable. Okay? So we simply take a snapshot of the database and we hard link out the files, or if it's going to a foreign file system, we copy them. But it's all lock-free. We don't have to lock the database to do this. So you can click a button and you have your backup. It's just done. So I'm really, really happy with that. And the other ones, there are slides for my talk yesterday, or I can talk to you privately if you want to know more about them. OK, so reflections. Retrospectively, I probably wouldn't have forked exist-DB. It made things quite difficult. So initially, we spent a lot of time trying to be very, very compatible with exist-DB, which we have achieved. But we did this by forking the data stream. So we had a version of exist that would write to both the B tree and to our LSM tree, and then we would compare the results and see if they were the same. And what we discovered is there were some bugs in exist that we didn't know about that we had to fix as well. So we spent a lot of time trying to understand whether problems that we were seeing were our problems or whether they were problems that we had inherited. And that is a hard thing to know, especially when you're trying to ensure correctness in a database. So retrospectively, if I had a green field, I would probably start a new project and create APIs that look exactly like exists. And I think that would be a quicker process than going the other way. So what's next? These are the things that we're currently working on. The ones nearer the top are the ones that we're working on right now. So we have a database. We believe it's stable. We believe we're not losing data. We think it has some nice properties. We think it's fast, but we don't know that it's fast, and we want it to be fast. So benchmarking is probably the next conference talk that you'll see me give. If anyone's interested in benchmarking, I'd love to talk to you. And you can read these for yourselves, so I won't do that. But thank you very much.
So thank you very much, Adam. And I suppose there will be a lot of questions because it's very interesting to hear about new XML database. So Mike K first. And then...
You talked about try-catch and sub-transactions. That implies you've got some kind of model for updates within try-catch and side effects, which seems to be something that was missing from the talk.
Yeah, so we have repurposed probably 80% of exist-db's xQuery engine for the time being. So we've inherited, exist-db has a xQuery update mechanism, which is not W3C spec compliant, so it doesn't use a PUL. So in exist-db, it immediately writes to the database. Obviously, we have a transaction here, and our updates happen in RAM until the transaction completes. So we have a kind of PUL, but it allows read your own writes. So if you do a read after a write in a transaction, you will see the writes that you made beforehand, but nobody else can see this. Ultimately, we want to replace the xQuery engine, which is our bottom point here. And yeah, expect more specs compliance there than we have currently.
So is there any other question? Okay, so if no, thank you again.